All right, let's dive into a physics question that seems, you know, pretty simple on the surface. But its answer? It reveals something really profound about how gravity actually works. It's a puzzle that's been on people's minds for centuries. So let's start with a classic thought experiment, one that kind of messes with our intuition. Picture this. You're standing at the top of a really tall building. You've got a heavy bowling ball in one hand and a light little tennis ball in the other. If you drop them both at the exact same time, which one hits the pavement first? So on one side, you have the bowling ball with a whole lot of mass, and on the other, the tennis ball with hardly any mass at all. Now, your gut, your everyday experience, is probably telling you the bowling ball is going to win this race, right? It just feels like the heavier thing should fall faster. But is that what really happens? Okay, to really get to the bottom of this, we need to strip away a big complication from the real world, and that's air resistance. So let's imagine we're doing this experiment in a perfect vacuum, where there's no air to get in the way. This lets us focus only on the pure physics of gravity and mass. Now check this out. This motion diagram shows us exactly what goes down second by second. At time 0, we let them go. After 1 second, look at that, they've fallen the exact same distance. 2 seconds in, they're still perfectly neck and neck. And then, bam, they hit the ground at the very same instant. This isn't a trick, it's just physics. So this is the real head-scratcher. Why in the world does this happen? I mean, doesn't it just make sense that gravity pulls harder on the heavier bowling ball? Well, here's the crazy part. The answer is yes, it absolutely does pull harder. But that's only half the story. Let's just get our terms straight. Gravitational force is simply the pull the Earth has on an object. And here's the key. That pull is directly proportional to mass. So the more mass something has, the stronger gravity yanks on it. There's no doubt the Earth is pulling way harder on that bowling ball. But this is where things get really interesting. See, mass has kind of a double life in physics. It doesn't just decide how hard gravity pulls on it. It also decides how much an object resists being moved in the first place. And we call that resistance inertia. You can think of it as an object's natural stubbornness. It's the property that says, hey, I like what I'm doing, leave me alone. And just like the force of gravity, an object's inertia is also directly proportional to its mass. The more massive it is, the harder it is to get it to speed up or slow down. This chart just lays it out perfectly. The bowling ball, it's got a huge gravitational pull, like a giant engine trying to make it go faster. But it also has huge inertia, meaning it's like a heavy freight train that's hard to get moving. The tennis ball, on the other hand, has a tiny pull, but also tiny inertia. The two effects are perfectly balanced. And this isn't just some neat idea. It's spelled out perfectly in the math. To see exactly how these two things cancel out, we gotta look at some of Isaac Newton's most famous equations. Okay, first up is Newton's second law of motion, which is a really big deal in physics. You've probably seen it, F equals ma. All it says is that the force you need to apply to something is equal to its mass times its acceleration. It's pretty much the basic recipe for how things move. Now, there's a specific version of this equation just for gravity. The force of gravity, F, is equal to an object's mass, m, times a special number we call g. And g is just the constant acceleration due to gravity. This formula defines that pull we've been talking about. And here is where it all comes together. In our vacuum, the only force acting on the ball is gravity. That means the F in F equals ma and the F in F equals mg are talking about the exact same force. So we can just set them equal to each other. And this right here is the aha moment. We get mg equals ma. On one side, we have mass related to gravity. On the other side, we have mass related to inertia. You notice anything they have in common? That's right. Since mass m is on both sides of the equation, we can just divide it out. It completely disappears. And what are we left with? This beautiful, simple little equation, A equals g. And what this tells us is something incredible. The acceleration of an object due to gravity has nothing to do with how heavy it is. It's totally independent of its mass. This was a revolutionary idea, first demonstrated by Galileo, and it's so fundamental that it even became a core principle in Einstein's theory of general relativity. How cool is that? Here on Earth, that constant acceleration g is about 9.8 meters per second squared. That means for every second an object is falling, its speed increases by another 9.8 meters per second. And it doesn't matter if it's a feather or a freight train, as long as we're in that perfect vacuum. So let's just recap the whole thing. 1. Gravity pulls harder on heavier objects. 2. Heavier objects are also more stubborn. They have more inertia. 3. These two effects, the bigger pull and the bigger stubbornness, cancel each other out perfectly. And 4. The result is that everything falls at the exact same rate. And that's it. That is why our bowling ball and our tennis ball end their race in a perfect tie. We started with what seemed like a simple question, and we ended up with a deep understanding of why it happens. It's not magic, it's just the beautiful elegance of physics. But this leads to another really interesting question, doesn't it? If everything is constantly accelerating towards the Earth, why do astronauts on the space station just float around? They're definitely still being pulled by gravity, so why aren't they falling? Well, that's a story about what freefall really is, and it's a puzzle for our next explainer.